this is Junichiro Horikawa, and this is the 13th episode for VEX for Algorithmic Design. And the topic today is trigonometry. Now let me first outline what I'm going to talk today. I'm first going to describe what trigonometry is briefly, then first explain about the differences of angles between the radians and degrees. Then I'm going to explain the basic trigonometry functions, which is sine, cosine, and tangent, and together with some exercises using them to draw some computational geometry. After that, I'm going to show you another type of trigonometry functions, which is an inverse type of a sine, cosine, and tangent, which is called as cosecant, secant, and cotangent. Then in the last, I'm going to also show you the inverse trigonometry, which you can use to estimate the angle from the cosine, sine, and tangent values, with some exercise as well. And let me first explain what trigonometry is. Trigonometry is a field in mathematics which explains the relationship between the edge lengths and the angle of the triangle. Meaning if you know the edge lengths of the triangle, you'll be able to estimate the angle of one of the edge on the triangles. If you know the angle and some other edge lengths, then you'll be able to have the leftover edge lengths from these informations. So by using it, you'll be able to estimate the shape of the triangle from a limited number of information. And this trigonometry is one of the essential mathematical field you cannot avoid going through, which is useful for many purposes, including mathematics and physics as well. And of course, for the algorithmic design to create a computational geometry. So in this video, there are tons of videos out there which explains the theory of trigonometry. So I'm going to pass that detailed theory of the trigonometry, but instead I'm going to show you how you can use this trigonometry by understanding the basics, of course, but to actually how you can use this as a tool for computational geometry for algorithmic design, so that you can use it for your own design purpose, for modeling purpose with a coding. So the key part in this video is to do the exercise what I'm going to show you. So please try to follow it. Now the first thing I would like to talk about is about the angles, how you express angle. And there are two ways to express angle. One is in radians and one is in degrees. And I believe most of the people are using degrees in order to express the angle when there is like a circle, and if you want to know this arc angle right here, you might say this angle is equal to 90 degrees. So this expression is a degrees. The way to express angle in this way is degrees, and the whole angle for this circle is equal to 360 degrees. So you can mostly express the angle between 0 to 360 degrees. So that's the degrees. Now when it comes to radians, it's a bit different. You still can express the angle, but when the degree is in 90 degrees, in radians, this is pi divided by 2, meaning this is 90 degrees. So the pi itself is 180 degrees. And I think you have heard about pi as a number from high school or maybe mid-high school, and which is equal to 3.1415 or something like that. And this value comes from a calculation between this edge, the length of the circle divided by the diameter of the circle. So let's say the length of the circle is A and the diameter is D, then the A divided by D is always equal to 3.1415, so on, and which is equal to pi. And this pi represents the angle as 180 degrees, which is this half arc. Now the point here is that in most of the computational programming languages, you use radians in order to express the angle. I mean, there are some languages using degrees instead, but in most of the cases, it uses radians to calculate, to express angles and use it together with some trigonometry functions. So even if you want to express the angle in degrees, you somehow have to convert it into radians in order to actually use it for the prepared functions in that computational language. And it is the same for the VEX language. The VEX uses radians for the angle. So that you have to remember about it. Although a funny thing about Houdini is that in VEX you use radians, but in H script expressions use degrees. So in the channel you have to use degrees in order to express angles, but in VEX you have to use radians. So that's a bit of confusing, but remember that there's two types of angle. Now fortunately there is a function in Houdini in order to convert an angle from degrees to radians or radians to degrees, so let's try that out first. First, I'm going to explain by converting degrees into radians, so I've just created the geometry node. Let's go inside and let's create a attribute wrangle with the detail run over. So attribute wrangle with the detail. Then let's first create some parameter channel to create some degrees. So let's say float degrees is equal to CHF degrees, and let's promote this channel, and let's set the range of this degrees from 0 to 360. Okay, so going into the edit parameter interface, I have clicked this one and set the range from 0 to 360 degrees. Now you have a slider which goes from 0 to 360 degrees. Now what I want to do next is to convert this degrees into a radians value, which if the degrees in between 0 to 180 degrees, it should be in between 0 to pi, which is from 0 to 1.3.1415, something like that. And if it's 360 degrees, then that's a 2 multiplied by pi, so which is going to be 6.28, something like that. So let's see if that's true by using a function in Houdini to convert degrees into radians. And to do that, first I'm going to create a detail attribute called radians, and then use the function called radians. And this function converts a value inside a parameter to a radians from degrees to radians. So inside here, I'm going to enter this degrees value. Okay. And as a result, you'll be able to see by going into the geometry spreadsheet, I can go here to the detail, and there you see this value which is expressing the angle in radians. So right now it is 360 degrees, so that is 2 pi, which is equal to 6.2819 and so on. If it's 180, you see 3.14159 and so on. So this is the really handy functions you use a lot in order to convert the degrees into a radians. Since most of us use angle and degrees, I think you're going to use these functions a lot. Now, there's also the other way around functions in order to convert radians into degrees, so let's look at that as well. So let's go back and Let me rename this first to degrees to radians. And next I'm going to create another attribute wrangle. For this one, I'm going to name this radians to degrees. For this one, I'm going to create another channel. Let's name this radians. And in order to convert this radians, I'm going to promote this. And in order to convert this radians into degrees, you can say, I'm first going to create a detail attribute called degrees, and there is a function in Houdini called degrees in order to convert a radian value into a degree value. So let's see how it goes. And currently the range of this radians is from 0 to 1. In order for you to make this range in between 0 to pi, for example, what I would always do is to use the value in between 0 to 1 and then multiply this by a constant value pi. So by using $sign and capital Pi, you'll be able to access to this constant value for the pi, which is 3.1415 and so on. And which is pretty handy. So when you want to create a slider that in order to control the angle in radians, I always do like this. So create an angle like from 0 to 1 and multiply it with pi so that you can have an angle between 0 to 100 degrees in degrees. In this case, from 0 to pi in radians. Okay, so, and if you want to have the range from 0 to 2 pi, which is equivalent to 0 to 360 degrees, then you can just multiply this by 2 as well. Okay, now let's see how it goes. Now, how this degrees in being expressed. Okay, now I forgot to make this detail. Okay, if I look at it, if the value is 0, then that's 0 pi, so the degrees is also 0. If it's 1 pi, if it's 1 multiplied by 2 pi, then that's 360 degrees. And if it's 0.5, which will be 1 pi, and that is equivalent to 180 degrees. So that's the method how you can convert from radians to degrees. Now this function is pretty useful. Both functions from degrees to radians or radians to degrees is pretty useful. So remember this. Remember how you can use this. So now that we know about the types of degrees, let's also try to see how we can actually estimate this pi itself with the calculations. And as I explained in the sketch, you can calculate this pi, the constant value for the pi, which is equivalent to 180 degrees, by dividing the length of the circle by a diameter of the circle. So let's try to see that in Houdini by actually creating a circle and try to get that parameter, the length of the circle, and divide it by the diameter. First, I'm going to create a circle. Let's set it to polygon and make the division as large as possible to make it look like a real circle. If it's too low, which it looks like a polygon, so let's make it high enough. And let's also make this as an open arc. Now, what I want to do first is to estimate the length of this circle, the parameter of the circle. And to do that, I'm going to just use this measure node, connect it to the circle, and set the measure to a parameter so that in the primitive attribute, you'll be able to get the length of the circle, which is currently 6.28215. And some of you might notice that this seems like already related to a pi value, which if you look carefully, this is the 2 pi value. So 2 multiplied by pi, is already a perimeter, and which can be calculated since the radius is currently 1, so the diameter is equal to 2, right? And if you divide this perimeter, which is currently a 6.28215 divided by 2, then the answer is 3.1415 and so on, and that is equivalent to a pi value. So you already have some hint here that what pi really is. Okay, and let's try to create some functions so that even if you have any kind of radius for the circle, you always get this pi value. So as a practice, right? Okay, so let's create a primitive wrangle so that you can access to a primitive attribute easily. And I'm going to name this estimate pi. Okay, and going back here. Now I'm going to create a primitive attribute called pi and calculate the division between the perimeter, which you have created from the measure node, divided by diameter of this circle. Now the diameter haven't been parameterized yet, so let's create a parameter to control the diameter of this circle. Okay, now I promote this diameter, which is currently in between 0 to 1. Let's set the range to 0 to say 5. Okay, and copy this parameter and paste it right here for the uniform scale for the circle. Now the uniform scale is used as a radius, so in order to convert the diameter into a radius, you have to multiply it by 0.5. Now let's see how it goes with the attribute. I would like to show the viewport as well as the geometry spreadsheet for this one. So let's split the viewport like from top to bottom here, and to the bottom view I'm going to set a geometry spreadsheet. Going into the new pane tab, inspectors, geometry spreadsheet, and to the primitive attribute. Now you see that there's a value called pi, which is set as 3.14108. Now it's a bit different from the original constant value, which is a pi equals to 3.1415 and so on, which is because of the resolution of this circle. So if you increase this division, more exact value you will get. So if you have lower quality of circle, like making this as like a polygon, you have a bit less accurate pi value here. So that's how it works. That's how you can calculate the pi. If you want to calculate the pi itself, you can do like this, but most of the cases you don't need to do this. You can just access to this $pi in order to access to the pi value, which is more accurate. I mean, that pi value is always constant, so this is already a preserved value. So in most of the cases you can just use this instead of calculating it yourself. But I just wanted to show you how you can calculate it by yourself. What's the relationship between the pi and the circle? Now that we understand the difference between the radians and degrees as an angle, let's talk about the trigonometry functions, which is sine, cosine, and tangent, how we can use this to express the relationship of the triangle information. Now first I'm going to draw an axis xy and draw a circle using center of this axis as the center of the circle. Now let's create a line from the center to some point on a circle, and from that intersected point I'm going to project it onto x direction and x-axis, and use this triangle to explain the relationship using sine, cosine, and tangent functions. Now from this triangle, you can extract 4 different informations. One is the angle of this triangle from the center of the axis, and one is the length of this edge from the center to the intersected point on the circle, which is equivalent to the radius of the circle. And you can also retrieve the y coordinate of this point here from the projected from the x-axis, and you can also retrieve the x coordinate of this point, and let's call this C, okay, and which is aligned with the x-axis. I say coordinate because if the intersected line comes here, and if you projected the point to this positions, then the coordinate becomes like this. And in this case, this point position is negative value. That is because we are looking at this coordinate, and this point is 0, 0. So on the left side is x value is negative, and to the right side the x value is positive, and the top side the y value is positive, and the bottom side, the bottom part, the y value is negative. So if you have a triangle, if you have an intersected point right here and have an intersection like this, then this point here is the x value is negative, and as well the y value is also negative. And if you have an intersected point right here, and if you projected this point to an x-axis, then in this case x coordinate for this point is positive, but the y coordinate is negative. So for value B and C, it is affected by where the point is located on a circle. So if it's on the right top positions, the B and C will be positive. If it's right here, the C will be negative and B is positive. This is negative for both B and C, and this is C is positive but B is negative. So that's how you use this B and C as a coordinate in this case, in order to express this information C and this information B. Now let me redraw this and start with a really simple example, which is this triangle. When B and C is positive and you have theta. Now sine function, cosine function, tangent function draws a relationship between those 4 information, and you can use this to express like this. So when you say sine theta, you use sine, cosine, tangent with a angle, this angle, and when it's sine theta, that is equivalent to b divided by a. So b divided by a is a sine function. Okay, and if it's cosine theta, that is equivalent to c divided by a. Sorry, c divided by a, yeah, like this. So that is equivalent to cosine. So goes like this, and if it's sine, goes like this, and if it's tangent, it's b divided by c. So goes like this. And if you look carefully to these functions, this indicates that if you know at least 2 information out of this 4 for this triangle, you'll be able to get the other values as well. Let's say if you have theta and a that you know, then in that case, if you use sine theta, you'll be able to estimate what b is by moving this b or moving this a into the left side. So in this case, a sine theta is equal to b. So you'll be able to get the v value here by having a and theta. If you want to know the value for c using a and theta, then you can use this cosine value, the cosine functions. So in this case, you can bring a to the left side and say a cosine theta is equal to c. So by having a and theta, you can also estimate what c is as well. Now let's say you want to get the theta value by having c and b. Now in that case, you can use tangent theta to estimate what the angle is by calculating the function for tangent theta. Now I'm going to explain how you extract the actual angle from the tangent theta later on, but you can also extract the angle itself by having two of the edge lengths, same for other functions as well. So that's how powerful this trigonometry is. You can estimate the other information about this triangle by having just two information out of this. And if you have an angle like this, if you have the edge from this point, the center to this point, then you have an angle like this, theta prime, and the projected x coordinate comes here. So let's say this is c prime, which is negative value. And a is the same, that is because that's the radius of the circle, and b could be a b prime. And in this case, b is positive. Now in this case, cosine theta prime is equivalent to c prime divided by a. Sine theta prime is equivalent to b prime divided by a. And tangent theta prime is equivalent to c prime, b prime divided by c prime. Now one thing you have to be careful is that when estimating this value for c edge, c coordinate and b coordinate and a lengths, you have to start the angle from the x-axis. So in this case, we're using this angle instead of this angle. So that's how it works. If you just use this angle here, then this c value becomes positive. So if you want to know this c as a coordinate instead of a length, then you should use this angle instead of this one. And it's pretty useful using this way because you can estimate the position of the circle, position of the point coordinate on a circle by providing the angle information, in this case theta information, which in this case, when you are estimating the c prime or b prime here, which is also can be expressed as a coordinate of this point on the circle, c theta and b theta, and this point can also be expressed as c b, and like this. So by calculating the cosine and sine, or cosine prime and cosine prime, you'll be able to estimate the point position on the circle. And if you look carefully to this sine theta and cosine theta, sine theta contains the information b here, which is the y coordinate, and cosine theta contains the information d, which is this value, and both of them have a value a in the bottom. And if you multiply this by a, then the bottom part will disappear, and in that case you also have to multiply it to the left side as well. This will become c and b, which is equivalent to the coordinate of the point on a circle. And the a is also equivalent to the radius of the circle. So meaning if you multiply radius multiplied by sine, you'll be able to get the y value, y coordinate of the point on a circle. And if you multiply radius together with the cosine theta, you'll be able to estimate the y coordinate. I mean the x coordinate of the point on a circle. And this understanding can be a really great tool in order to control the point position if you want to create a point position on a circle based on a circle. And in algorithmic design or computational geometry, this understanding is very essential. This is very important to know. Knowing it, you'll be able to create a lot of interesting geometries or shapes. And let's try to see how this works. This really works by writing some code in Houdini with the VEX so that we have more deeper understanding. So let's go to Houdini and let's first create some setup with the lines and a circle. Okay, first I'm going to create a line in an x direction, so I'm going to set 1 for the x and 0 for the y and z for the 0, and I'm going to keep the radius for 1 for now, okay, to make it simple. Next I'm going to create a transform node to control the rotation of this line so that I can rotate this line using z-axis from 0 to 360 degrees. And as I said before in the channel, instead of using radians, you have to use degrees. So in this case, if you say 90 degrees, you exactly type degrees in expressions. Or if you say 100 degrees, that's like this. Let's keep it like 45 for now. We're gonna later on make it per metric. Next thing I would like to do is to create a horizontal line projecting the end point of this line to the x-axis, and also create a vertical line. Okay, so to do that, I'm going to create a 2-point triangle connected to this this transform. One here, and I'm gonna copy one again and connect it to the transform. One for the horizontal line, I'm going to call it H line, and for the vertical line, I'm going to call it V line. Now let's go to the H line, and in order to project this point to the x-axis, you just want to access to the second point of this primitive, which you can check it by, first I'm going to make the guide point a bit larger, then show the point number here. So this is the number 0, this is number 1, so I want to access to this number 1 point and project it on x-axis. So if the ptnum at ptnum is equal to 1, then I'm going to set the y coordinate for this point to be 0 so that it will be projected on the x-axis to have a x line, the horizontal line. Now for this one, similar to what I have just done, if a ptnum is equal to 0 in this case, with this one, I want to project this one to right here so that it aligns with a point, the second point, which is a id is equal to 1. So in this case, I need to access to the point position information for this point. So before getting into the if conditions, maybe inside the if condition, I can first access to this point position right here. Vector npos is equal to 0.0p1, and the point that I'm going to update is this one. So point x coordinate, I want to update the x coordinate aligned with this one, this point, which is this point. So npos.x. So you have a vertical line projected from this point. Now let's merge these together. and also merge this one as well. And let's bring this transform to the first. So we have a merged 3 lines to create a triangle like this. Now I also would like to create a circle so that this point here is touching the edge of the circle. So the size of the circle should be equivalent to the edge length right here for the line, the initial line here, which is this line. So this line edge, this line's length should be the radius of this circle. So I'm going to copy this parameter, then create a circle. XY plane is fine. I'm going to paste the radius here, then connect it right here, and let's also set it as a polygon, set the division to 50, and set it as open arc so that we can see the edges. Now in order to get the information for the cosine, sine, and tangent for this triangle, using a theta, which is from this x-axis, we need to know 3 information. One is this length here, and one is the coordinate of this point for the y, and the x coordinate for this point as well. Now I can retrieve those information, this coordinate for this point, x coordinate for this point, y coordinate for this point, and the length for this one. By first of all, let's access to the x coordinate for this point by going into the h line point wrangle, and inside the pt num is equal to 1 conditions, which we were looking at this point, we can access to the x coordinate of this point. So I am going to use that and set it as a detail attribute. Set detail attrib, let's say c is equal to at p dot x. Okay, and if you look at the detail, now you have the c value here, which is the coordinate for this point, and for this vertical point, vertical line here, I'm going to access to the pt num equal to 1 again. So in this case, if at pt num is equal to 1, then set detail attrib at p dot y. Let's name this b, and at p dot y like this. Now that we have a v value with a this coordinate value for the y direction. Now this is positive right now, so this is also equivalent to the height of this edge. Now we also want to know the edge length of this a value here. This cannot be negative since this is the radius of the circle. So for this one, I can just say measure node and calculate the parameter. Now let's promote this to the detail by using attribute promote, and from the parameter to detail, I want to promote parameter, and just saying average is fine because there's only one value here. Now if you go back, the parameter is equal to 1 since this is the radius of the circle. If you change the radius, then this should also changes. Now I want to change the name to a. Alright, now that we have a, b, and c value here, let's go to the last one to see all those values being merged as an attribute, detail attribute. Now let's connect this merge node to an attribute wrangle, and I'm going to change the run over to detail and try to calculate the sine and cosine and tangent functions using those informations. Okay, so make it detail and access to the a and b and c first by saying float a is equal to f at a, float b is equal to f at b, float c equals f at c, Now, let's try by calculating the sine function first. So, the sine function was using this equations b divided by a. So, dividing this value with this one, this a value here. So let's try to see what the value is by actually calculating it. F at sine value is equal to b divided by a. Okay, and similar for a cosine value, that was c divided by a, and for the tangent, that was b divided by c. And let's see the result. And currently the value looks like these. Now we don't know if those are correct, but we can know that this is correct by actually using the function prepared in a VEX code, a VEX programming language, using sine function, cosine function, and tangent functions. So let's try to use those functions which is prepared in VEX and see if this calculation is really correct or not. Okay, and in order to do that, we need to use an angle in order to use those three functions, sine, cosine, and tangent. And currently there are no angle informations here, but if you go back here using this transform, you're using the angle right here. We are controlling the angle right here, so we need to access this information in order to use sine, cosine, and tangent functions for the VEX. So what I would like to do is to first create a angle parameter here, like this, promote this, and let's try to use this parameter to link with this angle right here, so that we can also use this inside this angle as well. Okay, so let's set the range for this angle. I want to use it as a degrees for user-friendly, to make it user-friendly, and convert it into radians inside of X. Because inside of X we need to use it as a radians. The angle should be in radians. Okay, so right now the angle ranges in between 0 to 360 degrees. Let's copy this value and go back to the transform and paste relative reference to link it. Now if you try to change this parameter, you can see that the triangle, this edge is rotating, and the projected triangles also been changing. And you can also see that the A, B, C, well, A is fixed, but B and C is changing, and the cosine value, sine value, and tangent value is also changing based on the position of this point right here. Okay, and let's see if this value is correct by actually using the sine, cosine, and tangent functions prepared in VEX. So sine value, I'm going to create another attribute called sine value 2, and in this case I'm going to use the sine function together with this angle information here. And this, for this angle information, I need to change this to radians, so I'm going to use the function that I've explained previously to convert the degrees into radians, like this, and use this angle inside a sine function. Same for other values. Cosine val 2 is equal to cosine ang. For f at tangent value 2 is equal to tangent value. Okay, and let's see if there are any differences or if those values are the same. And if you look carefully, cosine val and cosine val 2 is exactly the same value. Sine val 2 exactly the same, and tangent value 2 is exactly the same. So you can see that you can skip calculating these functions using those three informations by just calling this sine function, cosine function, and tangent function using VEX. But you can also estimate the other values if you only know the angle and one of the edge lengths, then you can estimate the other edge lengths as well using those two ways. One way is to use sine, cosine, and tangent functions prepared by VEX, and one way is to calculate a sine, cosine, and tangent value using those edge length relations. So let's say if you only know a value and you want to know C or B, and you also know what the angle is, then in that case, let's create another attribute for B. Let's go B2, and which can be calculated by this sine value here, or this sine value here, since we only know the angle, right? So sine ang multiplied by A. And using this calculation, you'll be able to get the B value, in this case, a height or the y coordinate of this point, which is equivalent to the original B coordinate, which is currently negative 3.7. Okay. Same for the C. F at C2 is equal to cosine ang multiplied by A, and you'll be able to retrieve the C coordinate for the X. And this understanding is pretty essential. The relation between the angle and the edge lengths. Now let's also try to change the radius of the circle, which is currently estimated as A, and which is set as 1 for now. Now let's create a parameter for the radius here, float rad, like this. And let's set the range from 0 to 5. Copy this, start with 1, and go to the line and set the line length with this radius value. Okay, now let's see how those values changes by changing this radius. If I change this, you see that A, B, C value, the edge length and the coordinate value for B and C changes, but those cosine value, sine value, and tangent value doesn't change. That is because these are the relationship, these are just expressing the relationship between the edge and the angle, but the edge length itself is changing. So you can say that these cosine, sine, and tangent value are kind of a relationship information, the ratio of how each edge size is dependent on the angle. Okay, by changing, so if you change the angle, you see the cosine and sine and tangent value are changing together with the A, B, and C, but just changing the radius doesn't really change cosine and sine and tangent value, because the shape of the triangle, the relationship, the ratio between the edge lengths is always the same, even if you change the scale. So only the coordinate value changes, which is an essential information when you are actually using trigonometry functions for your own purpose, for your computational design purpose. So by understanding this basic idea of this trigonometry function, sine, cosine, and function, let's try to use this actually for real practice. As I said, that the trigonometry, using trigonometry functions like cosine and sine, you'll be able to estimate the point position on the circle, which means you can actually draw circles using cosine and sine functions. So let's try to do that first as a basic exercise. Now let's create attribute wrangle. Let's set it to detail. Okay, and let's first set the number of points you want to create. You want to use to create the points to draw a circle as a polygon. So let's parameterize this. Okay, and let's set the range for this number from 0 to 100, I'm going to set the default value to 100. Okay, now I'm going to use the for loop to loop through the number of points that I want to create and create a point using @point function at some position. Now we haven't declared a position yet, so this is where we want to use a trigonometry functions in order to estimate the point position on a circle. Now in order to draw a circle, first you need to have a point information on a circle, right? And if you know all those coordinates for each point on the circle, then you'll be able to draw a circle trail as a point collection of points. Then later on you can just connect those points together with a polyline or something. Right, so the essential thing is to know the coordinate for each point, like x, y. And you can actually estimate this coordinate position by, if you know this angle information right here, and also the radius of the circle. And as I explained previously, when you calculate sine theta, the value is y divided by r. If it's cosine theta, then that is x divided by r. And if you want to know this coordinate x and y, then what you just need to do is to bring this r to the left side. So multiply r on the both sides, then in the right side the r will disappear, and the r comes to the left side of the equations, and as a result you'll be able to get the y value from r sine theta and x value from r cosine theta. So that's how you can calculate the coordinate for the point on a circle using the angle with the radius. So let's see if this actually works. Try now in Houdini with the VEX. Okay, so inside a for loop, we're going to create, first we need to have an information for the angle, right, for each point on the circle. And the angle is a bit in between 0 to 360 degrees, and in radians that is equivalent to 0 to 2 pi. So first I'm going to calculate a 2.0 by pi. Then we're going to divide this by a total number of points, which is this one, and then multiply by I. So this calculation will create a series of numbers which starts from 0 to 2 pi, since I iterates increment by 1 inside a for loop until a number value here. Let's end with the semicolon. Now that we have an angle, we can calculate the sine value and cosine value using the sine and cosine functions for using VEX function. So float sine val, or in this case we can just say x coordinate is equal to a cosine of an angle multiplied by a radius, and we don't have a radius yet, so let's also create a radius. So float rad chf rad, and let's use this rad variable as a radius, and float y will be sine angle multiplied by the radius. Okay, and let's use this x and y to create a position value. So x, y, 0, I'm going to set the z value as 0. Then use this position to actually add the point, and let's see how it goes. Now we don't have a parameter yet for the radius. Let's set the radius range from 0 to 5. And let's also name this drill circle. Let's see if I change the radius. You can see that I have just drawn the collection of points which is on top of the circle, a radius of 0.75 for now. And if I increase the radius, the point position just changes depending on the radius of the circle. And let's also try to create a circle to compare if the position of those points are correct. And let's set it to polygon, like division 50 open arc. And I'm going to copy this radius, copy this parameter and paste it to the uniform scale to use it as a radius. Now let's show this, and you see that the the point is overlaying on top of the circle, so we have just successfully created the points which is on top of the circle, the radius of 0.73. And even if I change this one, it's still on a circle like this. So this is one of the powerful feature of the trigonometry, using trigonometry to estimate the point position on a circle, which is pretty useful for many cases. To expand this basic knowledge, let's try to also create some animations using this trigonometry functions together with this circle information, that we can draw circle using those cosine and sine functions. What I want to try out here is to try to create some object rotating like an orbit, rotating around this circle like an orbit. So let's try to do that. First, I'm going to create an object that I want to rotate. Let's start with the sphere and set the size to 0.1 to make it small enough. Then I'm going to create a single point. I'm going to rotate this point counterclockwise and use this point to position this sphere, right? So let's do that. Since I have only one point, I can use either point wrangle or detail. I'm going to just use point wrangle. And let's name this rotate around, rotate, or let's say orbit. Okay, now first of all, in order to make this point rotated like a circle, we need to know the angle information. In order to use the cosine and sine functions to rotate the points, we need to know the angle to estimate the point location and also the radius. So let's create two parameters, angle and the radius, float radius. This promote, and let's set the range, the angle, let's say from 0 to 360 degrees, and for the radius 0 to 5. Now let's estimate the x coordinate and y coordinate, and just like what we just tried using the previous wrangle node. So that was x equals cosine multiplied by the radius, and the y was sine multiplied by radius. So let's do exactly the same thing here. Float x is equal to cosine angle multiplied by the radius, and float y is equal to sine angle multiplied by the radius. Okay, now let's set the point position for this point here, and at p is equal to set x, y, 0. Okay, now let's set the radius to at least 1, and let's also have a circle as a guide to see if it's really rotating around this circle. And let's copy the radius here, paste it to this uniform scale. Now I want to now if I change the radius, if I change the rotation of this angle, well, currently it seems like it's jumping pretty much. That is because I haven't converted this degree value into radians yet, so I need to do that by using radians functions here. Now it rotates from 0 to 360 degrees. Now let's use this point to copy this sphere using copy 2 points node like this. Now let's also merge this sphere together with the circle and see if, and let's also set the circle as a polygon with the open arc with enough divisions. Now let's go back to the orbit and change the angle, and it does rotates around the circle. Now you can animate this like accessing to some expressions based on the time using those frame values like f or ff divided by f end. ff is the current frame value and f end is this end frame value, so this division will create a value in between 0 to 1. And if you multiply this by 360 degrees, then and when the frame is equal to 1, then this value is close to 0, which in this case the frame starts from 1, so it is 1.5 degrees. If it's 300, if it's at the end of the frame, then the degrees become 360 degrees because the calculation here is equal to 1. So as a result, if you play it, you'll be able to create a loop animation based on the frame, which is another essential things when you want to create some motion graphics using cosine and sine and those time framed parameters or expressions. Now that was to draw a circle as an exercise. Now another exercise I want to show you is how you can draw a wave using one of the trigonometry functions. And actually you can create a continuous wave, which you see a lot when you see explanation for sine or cosine called as sine wave or cosine wave. So let's try to draw that as well inside Houdini. Now I'm going to again create a attribute wrangle, set it as detail. Let's name it as draw wave. Okay. Now first I'm going to create some parameters like a number of points that I want to use. And let's also create an integer value called switch to switch between the different waves for sine, cosine, and tangent to see the difference between those waves when using the different types of functions. So I'm going to name this parameter as switch. Okay, let's promote. Okay, it's gotta be parenthesis. Now for the switch, I want to set the range between 0 to 2 so that we have 3 options to change: cosine, sine, and tangent. For the numbers, we can have more points than this one. So like set it as 100. So let's go to the draw edit parameter interface for the switch from 0 to 2. And for the number, 0 to say 100. Now let's start drawing. First I'm going to loop through all the points with the number that I have specified. Oops. Curly bracket. Okay, first of all, as we did for the circle, we need to specify the angle for each point. And if we look at the sketch now, what we want to do is to create a wave like this one. And to create this kind of wave, we need to specify the point position for each point on the wave. And to calculate this one, to draw this kind of a wave graph, what you need is only the height information for each point. Meaning the y coordinate. For the x coordinate, it just increments to a positive direction. I mean, you can also go to the negative coordination, negative direction, but in this case, I'm only going to increment the x with the same value. Like if you set the step value by 1, then at each point the x will be incremented by 1. Okay. For the y value, we're going to use this x value as an angle and calculate the height. And that could be sine, cosine, or tangent. And each function creates different kind of graphs, and the very graph that I have just drawn here is coming from the sine wave. For the cosine and tangent wave, we can see by actually drawing it on Houdini. Okay. Now let's go back, and first we need to estimate the calculate the angle. So we'll create the angle values. So float angle is equal to, in this case we're not going to create a looped like a circle, so it doesn't have to be in between 0 to 2 pi or 0 to 360 degrees, but it can be expanded to an infinite number of angle. So in this case, what I'm going to do is to first create a pi multiply by 2, so that we have in degrees 360 degrees. Then do pretty much the same with the circle, multiply by I divided by num. Now this will create the range between 0 to 2 pi for this loop. But then I'm going to multiply another value for this. Let's name this as wave num as a float value. So if it's equal to 1, then you have whole one wave, which is from 0 to 360 degrees. If you set this as 2, then you have 2 waves from 0 to 720 degrees, so that you have so that with this wave num parameter you can control the number of actual waves. And it is also called as a frequency of the wave. You can control the number of the waves is equivalent to the frequency of the wave. And so we need to set this range more than 1. I want to set this range to more than 1, so let's set it to 0 to 10, so that in maximum we have 10 frequencies, right? Let's start with 1 though. Now that we have an angle, we can estimate the x coordinate and y coordinate. As I said, for the x can be just the increment value inside this loop. So I'm just going to set x value as angle. So each step, the angle incremented by I. So I'm just going to say, just going to copy this angle value to the x coordinate as an x coordinate. For the y coordinate, I'm going to use some functions, either sine, cosine, or theta, and I want to switch the values. I want to switch the functions based on the switch value here. So I'm going to start by 0, then use if condition with this switch value to switch between these 3 types of waves. So if switch is equal to 0, then I'm going to use sine wave for the angle. For the y coordinate, else if switch is equal to 1, then I'm going to use cosine wave, else if the switch is equal to 2, then I'm going to use tangent for the y coordinate. And let's see the differences. I'm going to create a position value vector cos set x y 0 and create a point at this point position. This. Right. Now currently the point number is 10, so there's only 10 points here. Let's increase the point number. Now we see that the one frequency, the wave with the one frequency have been created, and this is actually the sine wave when the switch is equal to 0. And if I switch this to 1, then the wave becomes like this, starting from a positive 1 as a coordinate, goes to negative 1. If you look at the geometry spreadsheet, you'll be able to see at the point attribute starting from 1, and at some point it goes close to -1 right here, and this should be somewhere around here, and then go back to a positive 1 in the end, close to positive 1. When it was sine wave, it was starting from 0, then goes up to 1 at some point, right, somewhere around here, and at some point it goes to -1, which is this one, which is equivalent to this position here, and then go back to 0 again, close to 0. So this is how the wave works for sine and cosine. If we change this to 2, I mean not this one, but if you change the switch to 2, then something more different wave happens, which is this is the tangent wave. And when the tangent wave, when the angle goes from 0 to, in this case, 180 degrees, it starts to go to infinite value. The y starts to go to infinite value. You cannot see the end right here. If you try to see where it is, I mean, this is not 180 degrees, but it actually is 90 degrees, sorry. So that is somewhere, we can check it by showing up the point number. So close to 22. So close to 22, 23, somewhere around here. So you see that at 0.25, the point position goes to infinite, or a really small, really high, I mean small value. It's a negative value, which is pretty far off the end. Cannot really see where it went, but somewhere around here it's just disappeared into the display in the screen. And if you think about it in the equations, it's easy to understand why it happens. If you have a circle and say this is the theta, and the calculation for the tangent was, say this is B and this is C, the tangent of theta was C divided by B. And when the theta goes to 90 degrees, like this, when the theta is close to 90 degrees, then B becomes close to 0, right? So dividing value by 0 gives an infinite value. So that's the reason why you have this kind of wave. So it makes sense. Now, computational geometry wise, from my personal experience, I don't use tangent wave that much, but instead I'm tend to use sine or cosine waves a lot than the tangent. But tangent is useful when it comes to estimate the angle, and I'm gonna show you that later on using the inverse trigonometry. So there are some usage for this as well in terms of designs as well. Okay, now that we have tried showing the waves, next thing I would like to do is to, again, like we did for the circle, like to create some animations so that the points run over this wave and a bit more information how you can control the frequency and also the step lengths. Now, one thing I didn't try out is to change this wave number here. So let's try that out first and go to the next one. Now, if you change this wave number, currently it's 1, and if you increase this, you see that the wave is going to expand to x direction. And if you set it to 2, now you have two same exactly the same waves, the sine wave, when the switch is equal to 0. If you set it to 3, now you have 3 waves, and so on. So by having this multiplication wave number parameter here, you'll be able to control the number of waves, how many waves you want to have. Like this. And making it as a float, you'll be able to control the numbers more precisely, or with the decimal values, so it's pretty useful in some case. Now, just like what we did for the circle, let's try to use this sine wave or cosine wave to move those points on top of the wave and animate it as a practice. Okay, so start with creating a sphere, set it as 0.1. Okay, and then I'm going to create a single point starting from 0, 0. Then I'm going to use a point wrangle to move this point on a wave. Like now I need two information. One is the angle, one is the you could have another values like radius, but maybe not. Let's just go with an angle itself. Okay, and x can be just the angle, and y could be a sine of angle. We're gonna just test with the sine wave. Okay, and then at p can be created using x and y. Okay. Now, let's also promote this angle, and what I want to do here is to use copy to points to move this sphere on the position of this point here, and then try to animate this sphere moving like a wave. Okay, to do that we need to change this angle here. Currently it's from 0 to 1. I want to set it as degrees so that it's easy to control. So let's set it as, let's say, 360 degrees. And since we are using this as a degrees, we need to change this to radians inside the VEX. So say radians. Now that we have a point moving like a wave from 0 to 360 degrees, now if you want to animate this one, we can do the similar stuff we did for the circle, animating on the circle. FF divide by F end multiply by 360 degrees. And as a result, you'll be able to create animation of the sphere running on top of the wave for a single wave. Now the point here is that if you multiply this by 2, you are increasing the range from 0 degrees to 720 degrees. So as a result, you'll be able to have 2 waves. So if you say multiply by 5, you'll be able to have 5 waves in one sequence from the first frame to the end frame. And so this idea is pretty useful when it comes to animate using a wave function. Currently in this case, using the wave function, the point is moving to the x direction continuously, but you can multiply this x value by 0, meaning this coordinate becomes 0, and as a result you only see this up and down animation, and by looking at it you might be able to imagine that this continuous animations going from +1 to -1 can be used for many other purposes, and I'll show you other example how you can use this for other purpose. Before going in, let's see why we are having the value in between -1 to +1 for the sine function, and that could also be said for the cosine function as well. Okay, so let's say we have circle this, and when the angle is equal to 0, then a value is always the same, it's the radius of the circle, and the b value here, which was the height, the coordinate, the y coordinate of this point, is 0, and the c, which was the x coordinate of this point, is equal to a. Right? So in this case, the sine theta, which means in this case sine 0 degrees, is equal to b divided by a, and since b is equal to 0, then that is equal to 0. So it starts from 0, right? When it's 90 degrees, then in this case c is equal to 0 when the point is right here, but then the b becomes equal to a, right? So in this case, b divided by a means a divided by a, and that is equal to 1. So that's the reason why in 90 degrees the sine wave will give you +1. Now when the line comes here, when the points intersected at this point, then the angle is 180 degrees. Now in this case, c becomes -a and b becomes 0. Since for the sine we're using b again, so the value becomes 0 again for the sine. Sine 180 degrees is 0. Now for this point, this time the v becomes -a and c becomes 0. And since we're using b here, and this is going to be -a, so the result of sine 270 degrees is equal to -1. So you can see that the value goes from 0, 1, 0, -1, and 0, back to 0 again. So this indicates this kind of wave. Starting from 0, becomes 1, becomes 0 again, becomes -1, becomes 0 again. And this 0 value and this 0 value is equivalent here. So when we reach here, another same wave starts to happen. So this is how the wave works, and this is similar to cosine. If it's cosine, when the degrees is equal to 0, then cosine theta was c divided by a. So c the initial c value here when the theta is equal to 0 is c is equal to a. So in this case, a divided by a, so becomes 1. So that's why a sine, the wave for the cosine starts from 1 and goes to 0, -1, 0, and 1 back to again. So this is one range for the cosine wave. So you can say that the cosine wave and sine wave is pretty similar. It's just half pi offsetted. So if you offset the sine wave just 90 degrees to the left, you have this same wave that you have right here as a cosine wave. Meaning you can also say that sine theta plus 90 degrees is equal to cosine theta. So that's how it related in terms of the wave functions. Okay. Well, you don't really need to remember how this related, but remember that it's a good idea to remember that when you use sine, when the value always starts from 0 when creating a wave from 0 to 360 degrees, and the cosine always starts from 1 when the angle is from 0 to 360 degrees. And the range is always in between 1 to -1 when you calculate the sine and cosine functions. So that's the essential part, essential thing you might want to remember to use it as a tool. So having that kind of information, let's try to use an animated sine function or cosine function for other purposes, like try to control the scale of the geometry like a wave. Okay, so let's start by creating a sphere, and I'm going to make it a polygon. Let's have like 5 frequency here. Then use a point wrangle to control each point of this polygon. Let's name this wave scale. Okay, and what I'm going to do is to use sine function with the time value as an angle to control the scale of this sphere so that it will grow bigger and smaller, bigger and small, like a wave. So first let's create a scale value, and what let's just call this value, and I'm going to use sine. And inside the sine, since I want to go back and forth based on the frame, I'm going to first retrieve, like I did in the expression, I'm first going to retrieve the frame value and divide it with a f_end. You can access to the frame end value like this, $fend. For the frame, you have to type like this @frame. So it's a bit different from the expressions, but it's how it is inside of VEX. Okay, and also I'm going to multiply with the pi multiplied by 2. Since we are dealing inside of VEX, we cannot use degrees, but instead we need to use radians, so that's why we're using pi. And pi multiplied by 2 is equivalent to 360 degrees. So currently we have just created the angle value between 0 to 360 degrees changed by the frame value. Okay, now let's change this value. Currently the values range is in between -1 to 1 using sine. That is because I'm using sine function. So to make it, but I don't want to use negative scale for negative value for the scale value, but I want to set the range something like 0.1 to 1, say. in that case, we need to remap this value, which is in between -1 to 1, to a new range. To do that, we can use a function like a fit, which is a functions in a VEX in order to remap one value from one range to another range. So in this case, we want to remap this value, which is currently inside -1 to 1. -1 is the minimum, and +1 is the maximum value. And we can set this to a new range, which I want to set the new minimum to 0.1 and the new maximum to 1.0. As a result, we can use this value as a scale value. To actually use it as a scale, we can multiply the point position with this value. Okay, let's see. Now the point has, the scale has already been changed, and if I play it, you can see that the scale is changing over time, and it's going from small to big to small again, and creating like a wave animation. So this is one of the way you can use sine function or cosine function together with the time to create an essential animations, looped animations like this, or wavy animations. And if you want to make this quicker, to make this animation quicker, you just need to multiply this value inside a sine, like by 2. You can now have two wave frequencies within this frame range. That is equivalent to 0 to 720 degrees, which makes the scale animation faster. So if you say 5, you have more faster animations like this. So that's one of the basic example how you can use wave, sine wave or cosine wave. You can also change this to cosine wave. But the overall animation, it looks the same because it's just a 90 degrees shifted value. The only difference is that it starts from a different value. So that's how we can use as a basic exercise. So I hope you understand the basic idea of how this sine and cosine function would work together with a time value to create some interesting looping animation. And this very idea could be expanded for many other purposes, so which is really useful and powerful. So please try to remember how you can use this. Now that you have a basic understanding of the basic trigonometry, I would like to introduce you to some of the other trigonometry functions, which is called as secant, cosecant, and cotangent, which is actually just an inverse functions for the sine, cosine, and tangent functions. So it's pretty much similar to what we have just done, but the wave shape is going to look a bit different, and I don't think you're going to use those functions that much. So, and the VEX doesn't really have those inverse trigonometry functions, so you don't really need to remember it. I mean, it's not really necessary to remember it, but just want to show you what these are about. Okay, so I'm going to start by creating an attribute wrangle. Let's name this CSC, sec, and cot. I'm going to introduce you 3 different other trigonometry functions, which is an inverse of sine, cosine, and tangent. Now let's start by creating an angle and create a parameter like an angle. Let's set the range from 0 to 360 degrees. Okay, now let's also change this, convert this into radians, like we always do in order inside of VEX. Now, the first thing I'd like to show is the cosecant. And it is often expressed as CSC in programming languages. Although in VEX we don't have this function, so I'll just call it cosecant. And it is calculated by dividing 1 by a sine of an angle. So this is just it. This cosecant is just an inverse value of sine value. So that's just it. And for the other value, it's pretty similar. The value called secant is a inverse value of cosine, and f at cotangent is the inverse value of tangent value. So that's just it. In some cases these values are useful, but most of the cases you just need to remember those sine, cosine, and tangent, because these inverse value can just be calculated just by creating the inverse of this sine, cosine, and tangent. So you don't really need to remember those names, but in some cases when people explain, some people use these names to express this inverse numbers. So it's just for your reference. When you see this for first time and you don't know what it is, just remember that it's just one of the inverse number of sine, cosine, and tangent. It's nothing more than that, right? And let's look at the detail attribute and see how numbers changes. And the difference between the sine, cosine, and tangent with these cosecant and secant and cotangent is that for any other values here, for every values listed here, all these values will give you an infinite number, because for all those values there is a chance that you get the value 0. So all these values will give you at some point an infinite number. So we could see that actually by drawing a wave using these values, like we did for the sine, cosine, and tangent. So let's try to do that by just copying the one that we have used to draw the wave, which is this one. So I'm going to copy this one, bring it up right here. And for this one, we were drawing the wave for the sine, cosine, and tangent, but instead we're going to replace this with an inverse of these values. So 1.0 divided by sine, which is the cosecant, 1 divided by 0 by cosine, which is the secant, and 1 divided by tangent, which is the cotangent. And as a result, when its switch is equal to 0, then that is cosecant. You'll have a wave looks like this. If it's 1, it's pretty similar to the cosecant. Secant and cosecant is pretty similar. It's still a half 90 degrees shifted wave. When it's come to a cotangent, it looks a bit different. Let's set the wave number to 1. It's pretty similar to the original tangent wave as well. If you make it back to the original tangent value, it looks like this. If you divide it by 1, if you have an inverse value, it looks like this one. So that's just it. I'm gonna set it to... Now I don't use these functions that much, these inverse functions that much. I just wanted to show you the name, how what these names stands for, and I just wanted to show that these are just the inverse number of the sine, cosine, and tangent. And in practices for a computational design, you don't use these values that much. I mean, there are chances that you use inverse number of sine, cosine, and tangent, but most of the case you don't use this name that much. But it is only the reference for you to know that these values stands for an inverse when you look at some papers and so on. When you see this name. Now let's go to the last topic, and the topic that I want to show you in the last is how you can estimate the angle from the edge lengths. There are chances that you only know the edge lengths and you don't know what the angle is for those edge lengths. In that case, and there's just a function to retrieve those angle value from the edge lengths of the triangle. So let's see what that is. The first thing I'm going to do is to copy one of the node that we have created previously, which is this set where we have created a circle with the triangle where we can control the angle, and all those values has been stored inside the detail attribute. So I'm going to copy this one as a basic set to estimate the angle from the edge lengths. Okay. Now that we have just copied it, and let's name this ST angle. Now what I want to do is to say that we don't know what the angle is. Well, currently we do have this parameter here, but let's say we don't know that value, but we only know the edge lengths for A, B, and C. A is here, and B is the height coordinate, or this point coordinate for the Y, and the C is the X coordinate for this point here, or point here. Okay. So those are the value that we know, but other than that we don't know the angle. But from those three values we want to estimate this angle value, and we can actually do that by using a so-called inverse trigonometry. The previous one that I showed you is not the inverse trigonometry. This is the inverse value of a trigonometry functions. But the one that I'm going to show you is called as inverse trigonometry. It is a kind of a different stuff which have a different name for the functions, and each one is used to estimate the angle from a sine or cosine or tangent function values. And in order meaning that having the value for the sine or cosine and tangent, you'll be able to estimate an angle from those values. For the sine, you can use a function called arcsine to estimate this angle for this from this output. For the cosine, you can use one called arcsine, and for the tangent, you can use so-called arctangent. So let's try to see how we can use that. Now, since we already have the value A, B, and C, which is this one, right? Which is this one, and we also have let's say we also have calculated the sine, cosine, and tangent value with these equations here. Let's remove those. Okay. So we have three values for the sine, cosine, and tangent. Now what we want to do is to estimate the angle from those values, and we can use that by using inverse trigonometry functions. And if you have a sine value, then what you can do is to calculate the angle using a arc or a sine function. A sine is same as an arc sine. It's also an inverse sine of the argument. And inside this parameter, you put the sine value calculated by b divided by a. And as a result, you'll be able to get the angle value used for this sine wave, a sine function. And let's promote this to a attribute. And as a result, we have got the sine value saying 0.7749. Well, let's convert this to degrees so that it's easier to see what the angle is. So let's say degrees. Now it says 50.8. Now it looks like it's a bit different from 128.2, but I'm gonna explain why that is later. Now let's also calculate the cosine angle. Cos ang degrees a cos. So arc cosine is typed as a cos, and use it for a cosine value. This one will give you a 129.2, which is equivalent to this angle here. Now let's see another one. F at tan ang is degrees a tan f at tangent value. And as a result, you'll get minus 50.8. Now let's see what those angles means when we calculated the arc or inverse trigonometry of those sine, cosine, and tangent here. Now let's look at the sine angle first. This one, f at sine angle, and let's focus on this value here by changing the base angle and see how this changes. And you can see when it starts from 0, the sine angle is also 0, and until 90 degrees, the value for the original angle for this one and this angle here is the same. But after 90 degrees, the value becomes decreasing. The value is decreasing until 180 degrees. So that means when we use sine, arc sine, what we get as an angle is this angle here for the triangle. Not for this angle, but the angle which is in between these edges. One for the center to the point on the circle, and one is the edge, which is the projected from the center to the projected point on the x-axis. So that's the angle that we're going to get when we use sine, arc sine. And if we go to more than 180 degrees, then now the angle becomes negative in this case. And go back to from 270 to 360 degrees. It still is calculating this angle, but multiplying by -1. So when we use arc sine, when the angle is between 180 to 360 degrees, the value for this one becomes negative, and it only calculates the angle between this projected curve, projected edge, and the edge on the circle. And one of the points of the edge ends on the circle. So the value for the angle that we could estimate using this arc sine is a bit limited from the original angle. We do have an angle even though we have like a various angle from 0 to 360 degrees, just by looking at the arc sine, we'll get a limited information about this angle. If we look at the cosine, arc cosine value, which is this value here. If you look carefully, from 0 to 180 degrees, it looks pretty much the same with this value here. If you go more, it starts to decrease and go from 180 degrees to 0. Now this value, this cosine, arc cosine doesn't give you a negative value, but the range is still limited. It's 0 to 180 degrees. And if you look carefully what it really means, it uses this x-axis as the base axis, and from 0 to 180 degrees, the angle is between this x-axis, between this angle, this line projected to the circle or intersected to the circle. So we are always getting this angle here, 0 to 100 degrees. When it goes more than 180 degrees, what we get as an angle is not this angle here, but actually angle right here. So the angle we get is always in between 0 to 180 degrees. So if we wanted to know the angle from 0 to somewhere around here, like 208, you cannot use cosine, arc cosine as well, since this is a bit limited as well as the arc sine. Okay, and if you look at the arc tangent now, which is this one, and the attribute tan ang, which is this one here, and let's see how this changes. If it's 0, it starts from 0. If it's raised up until 90 degrees, it's still the same as other values. Now after 90 degrees, it becomes minus 90 degrees. It flips to minus, if it's the negative for the left hand side, and starts to decrease. And if it goes more than 180 degrees, it starts from 0 again and goes up 90 degrees until 270. Then after this goes back to negative 90 again and goes to 0. So honestly speaking, this cotangent, or arc tangent result is most difficult to read as a result. In order to use it for your practice, it's a bit hard to use because it's not really straightforward value in terms of the value that based on the position of the point. So even though I said that those inverse trigonometry functions can be used to estimate the angle, the actual angle you get out of this arc sine or arc cosine or arc tangent is kind of limited. But fortunately, there's other functions, inverse trigonometry functions, in order to estimate the angle, which can be used to estimate the angle between 0 to 360 degrees. That's what we really wanted to know. So I'm going to show you what that is, and that is called as arc tangent 2. Using that function, you'll be able to calculate the angle between 0 to 360 degrees, and that's the most used functions in order to estimate the angle from the edge lengths, and I'm going to show you how you can use that. Okay. Now to use that, you just need a coordinate for this point right here. And you also need to know where is the x-axis. In this case, the x-axis is 1, 0, 0. So it's pretty straightforward. And this coordinate right here currently is expressed as b and c. The b is the y coordinate and c is the x coordinate. And can be expressed from +1 to -1 for both b, c value. Now, to use those BC with the arctangent 2, you use like this. So first I'm going to create a tangent angle tan ang 2 and convert the angle that I'm going to estimate to degrees. Then use a function called A tan2. For A tan2, you need to specify two parameters. One is the y value and one is the x value. Now the y value is in this case b and the x value is in this case c. And as a result, the value that you get, tangent 2, can be used to express the angle between 0 to 360 degrees. Now let's see how it works. Currently the angle is 60 degrees. If let's start from 0, so it goes up until 180 degrees. Now you can see that the tangent angle 2 is raising up until 180 degrees, and after 180 degrees it switched to minus 180 degrees. But actually this minus 180 degrees is equivalent to a 180 degrees, because that's just the difference between if you calculate an angle from counterclockwise or clockwise. Okay, if you raise up more, you see that the negative value is increasing, but that is also equivalent to this value here. This value from 0 to 229 or 240, let's say 245, and currently it says negative 115, but that is equivalent to 245 as well. If you add this negative value by 360 degrees, you get the same value. So even though it looks like it's the different number from this value, it's still the same. The value it's expressing is the same value. So you are actually getting the value in between 0 to 360 degrees. Like this. And this function is pretty handy. I use this a lot myself to estimate the angle between two vectors. even though if it's in the 3D space, and even though you don't know where the x-axis is, you can still estimate the angle between two vectors. And I'm gonna show you how you can do that as a final exercise. Okay, so remember that you can use this arc or inverse trigonometry functions to estimate the angle. Most of the cases I use this one, but if you only need to know the angle between 0 to 180 degrees, then you can use like arc cosine or arc sine or arctangent. Maybe you don't use this arctangent that much, so maybe either arc sine or arc cosine. But if you have more information, if you need more information, arctangent 2 might work better for you. Okay, so let's try to use this as an exercise, and let's end this topic or session. Now let's first create two lines to estimate the angle between. So I'm going to create a two line. One is facing z direction or y direction, and one is facing x direction. So let's set this as an x directional line. So currently the angle between those two lines are 90 degrees. Now I also would like to create a transform node so that I can rotate it freely to have a various angle between those two lines. Okay, so one transform here, another transform to the another line. And now I'm going to merge these two lines together and try to estimate the angle between two lines using some VEX coding. Now I'm going to use another detail attribute. So first I'm going to create a attribute wrangle and set the run over as detail and set angle for the arc. Now let's first have some parameters in order to control the angle for these two lines. Though, well, what I really want to do is to estimate the angle between those two lines, so I don't want to show that up inside the code because that's going to be a cheat, right? So I'm going to create a parameter, just a parameter, which I'm not going to access using the code inside the code. I'm just going to use it in order to control the rotation for this one, the initial rotation. So I'm going to create two float values. One is ang1, or let's just say it could be a random seed, so that we don't actually know what the real angle is, right? So seed 1 and the other one is C2. Right. Apply. Okay. Now let's look at those. Now let's have this as a degrees. So I'm going to set the range from 0 to 360 degrees. Or I mean, this is the seed, so it doesn't really need to be an angle value. So I'm going to copy this parameter, then go back to the transform, and for this for the first rotation, let's say I'm going to control the y rotation, so if rotating this way, and using the seed together with the random function, and inside a random I am going to paste what I have just copied, which is random seed. So as a result, you'll be able to create a value between 0 to 1, random value between 0 to 1. So I'm going to multiply this by 360. Right. I'll do the same thing for the other transform. Now let's copy this value and bring this to a second transform, and for the second transform I'm going to try to rotate it with the x-axis. Right. Now and let's use the different seed. So in this case, this seed 1. Okay, so now we have two seed connected to those random seed value for the transform, the first transform and second transform, and if I change this seed value, I'll be able to change the angle randomly between those two lines. Okay, so the setup is good. We now have a information how we want. Now we have an information. Now we can try how we can estimate the angle between those two lines. And to do that, I'm going to use the specific functions, the inverse trigonometry functions, what I have just shown you, which is an arctangent function, arctangent 2 functions. Okay, so to do that, first we need to know the vectors between two lines, the vectors for each line, and we also need to specify the x-axis in order to calculate the angle here. Now, what I mean is that from now until this point, we were only dealing with the two-dimensional plane, right? So we only had x and y coordinate, but the one that we are dealing with here have a additional dimension called z. So we are dealing with 3 dimensions, and in this 3 dimension we have 2 lines like this, and we don't, this coordinate for each point could be x, y, z, and this one is x, y. So the difference is that we have additional coordinate here for the z here, which makes a bit difficult, which makes a bit more difficult in order to estimate the angle between these 2 lines. But you can actually do that. I mean, previously we were using this x-axis for the base in order to calculate the angle, but what we can do now is to use one of the vector, either this one or this one, as a base axis. So say you want to use this axis, this vector as the base axis, and say this is capital X, and using this as a base axis to calculate the angle between the vector for the other vector. By doing it, you'll be able to estimate any kind of vectors which is on the 3D space using the same function, like A10(2). And to do that, let's say this is the x-axis, but and on the 3D space, so maybe I'll just call it A, right? And there's a vector that you want to calculate, estimate. I mean, there's a vector that you already know what the value is, and you want to estimate this theta. What you can do now is to know the x and y values in order to use it with the A tangent to functions. Right? So this is the parameter for the function y and x. And previously, when the coordinate was x, y coordinate, it was pretty easy. We were just using this x-axis as a base and use the projected point, this coordinate as a x coordinate, and this height as a y coordinate, and place this value into this parameter, and as a result you'll be able to get this theta value. But in this case you don't actually have, I mean, this is not on the xy plane, so what you can do is to consider this a-axis as a virtual x-axis and project this vector onto this a-axis like this, so that this will be 90 degrees. And this is pretty easy to do. I mean, we have done this thing from our previous sessions, which is by using a dot product. Okay, using dot product, if let's say the axis is normalized and you want to know the length of this size here, let's call this C or P as a projected length. Okay, this P can be estimated or calculated by P equal dot or B dot A, and A is normalized, so the length is equal to 1. As a result, what you get is this projected length of this vector B. And if you have this P information, the projected length here, you'll be able to create this vector as well, right here. You just need to multiply this A, the normalized vector A, with P, and you'll be able to create this vector. And if you have those two vectors, you'll be able to estimate the length for this height as well, which can be estimated by calculating the power of P plus H, power of 2 for H equals to the length of B multiplied by the same value, so the power of 2, which is, this is B, right? So if we are looking at the triangle with the one of the angle being 90 degrees, then this kind of equation can be used. P multiplied by P plus H multiplied by H is equal to the edge length of V multiplied by the edge length of V. Right? So as a result, the H can be calculated as P, or B minus P divided by, or square root of those subtraction. Right? And then you'll be able to use this as a y value and this as an x value to calculate with A tangent 2, and as a result you'll be able to estimate the angle between two angles, between two vectors. Shall we try this, if this really works or not? The first thing first, we need to know two vector informations, right? So let's get that, and to do that we need to access to two primitives. Okay, so let's first access to this first primitive, and from the first primitive I would like to access to 2 points of the first primitive. So for this one, and for this first primitive you have 2 points, obviously, because it is just a line. So let's try to get those 2 points using a function called prim points. Using prim points, you'll be able to get the points constructing this primitive, and at 0. So 0 means the first primitive, and I'm gonna call this PTS1 and array. Now let's also get the second primitive by changing this to 1. Let's set the name to 2. Now from each of the array we're going to retrieve 2 points. So let's say for the first one I'm going to call it PT11, which is the first index from the array PTS1, and PT12 is the second point, and I'm going to retrieve the point position from each of the point number. Like this. Now calculate the vector from the first point to the second point by calculating the subtraction, and let's name this direction 1. And we know that the length of the line is equal to 1, but just in case I'm going to normalize this so that the length will be forced to be 1. Alright, now let's do for the second one. I'm just going to copy all these and rename this to 2122 PTS2, PTS2, and position 21, position 22, and direction 2 is a subtraction between position 22 minus position 21. And this should also be 22, 21, and 22, right? Now we have created a 2 vectors, direction 1 and direction 2. So one of the direction should express one of the lines here, and one of the other one express the other lines. Right. Now what we want to do here is first of all calculate the dot product between those two vectors. Let's see how we do that. So first of all, float dot is equal to dot direction 1, direction 2. Okay. Now that we have retrieved the projected lengths for direction 1 to a direction 2, or direction 2 to a direction 1, and we can use this. You can use that as a p-value here, right here, which is the dot product between two axes, two vectors. And let's say I want to use this direction 1 as a axis, right? Now, the next thing I would like to do is to calculate the length for the h here, right here. And to do that, we need to know the lengths for the other vectors, direction 2 in this case. And currently, we have normalized this, so the size is equal to 1, but in this case we shouldn't normalize this. So what I'm going to do here is to say the b length is distance between the position 1 to 1 and position 2 2, so that just in case this length well, although I could just use the length of direction 2 as it is, because this is also normalized. If you don't normalize this, then you need to calculate the distance. So maybe it's better we don't normalize at here for both direction 1 and direction 2, but for when we calculate the dot product, only for the direction 1 I'm going to normalize this, so that I want to use this direction 1 as an axis, base axis, to calculate the angle, right? Now, for the length for the direction 2, I can just say length of the direction 2 to get the magnitude or the length or the size of the vector. Now that we have two informations, the dot product, which is the projected length for a direction 2 to a direction 1, and the size of the direction 2, we can estimate the size of and height by, first of all, calculate the power of 2 for the len and dot product, and subtracted like this, then calculate the square root like we have done here. This. Okay, now that we have an h value and a height value, we can use this as a y value, and we can use this dot product as an x value for a arctangent 2. So let's try to estimate the angle here. So angle is equal to a tangent 2, and the first parameter will be y, so h, and the second one will be dot. Okay, and let's have this as a degrees, as in attribute. So since we're in detail, I'm going to create a detail attribute. So angle is degrees angle. Okay, so let's again split the panel from top to bottom, and in the bottom panel I'm going to show up the geometry spreadsheet for the detail. And there you go, there's an angle here, and currently it says 130 degrees and looks like it is. Let's try to change some parameters here. Let's see the changes. So currently this one, it says 44. And if we do like this, it says 87. Now we don't really actually know if those values are correct or not. So let's see it by changing this value to the constant value instead of the random value. Okay, so to do that, I'm going to create a switch node, or maybe for this one, and create another transform node connected to this line, and do the same for the right one. Create a switch, create a new transform node connected to the switch, and currently, and also let's copy this parameter and paste it to the switch, select switch parameter, so that those switch values will be linked, and change the switch value to 1 for now, so that the right hand side transform will be used. Now going back, and currently the angle should be 90 degrees because I haven't rotated anything. And if you look at this angle here promoted to the detail attribute, it says 90, so it looks correct. Now if I rotate one of the angle here, let's say this one to 45 degrees, it doesn't seem to change. Alright. Okay, I think I should rotate for the Y. Or maybe for the X, Z. Okay, so I have used the Z axis to rotate this first line, so the angle between those two lines should be 45 degrees. And let's see if that's true by looking at it. Yes, it does look like so. And also let's try to rotate the second one. Let's rotate this 90 degrees. Now it becomes 90 again. If we look at it, it says 90. If we rotate this by 135, the angle should be somewhere around 135. So if we go look back again, oh, it says 120. I guess that's because combining this 45 degrees with 135 degrees, the actual angle between those two lines became 120. So it seems like the degrees to angle that we are getting using those two for those two vectors are correct using those methods. So that's how you can estimate the angle between two vectors, even though in the 3D space. Now that we have estimated the angle between two vectors, what I want to do as a final exercise is to use this angle information, and together with those vectors I would like to create or draw an arc connecting one of the edge to the other edge using these vectors as a plane information, and especially without using like transforming functions, but only using cosine and sine trigonometry functions. It's going to be a bit more advanced things, and you don't actually need to use cosine and sine functions to draw that, but if you know how you can draw this arc just by using cosine and sine, then you are really I think you have enough information to use those for many purposes, for computational design purpose. So let's see how we can actually do that. Now previously, when we were drawing circle or arc, we were only dealing with the x, y, 2D axis, right? And that was pretty easy to deal with because the point information can be described using a cosine theta and sine theta multiplied by a radius. But when it comes to 3D, it's going to be a bit more harder. It's going to be a bit more difficult to express this circle. So let's say the axis, we have axis x, y, and z. And you have an arbitrary plane here with the two vectors, v1 and v2. And what you want to do is to create a arc at this point, just by using the angle and cosine and sine. Now how do we do that? Actually, if you try to think this plane as a 2D, it starts to become a bit more simple. Just like what we did in order to calculate the angle between two 3D vectors. We can estimate one of the vectors as a virtual x-axis. So say this v1 becomes a virtual x-axis. And this v2 is, there's also a virtual y-axis somewhere around here. And this v2 is on top of this xy, virtual xy plane. And there's a virtual circle which can be drawn on top of this virtual plane. Now it starts to become more understandable. The value that you get out of the cosine and sine is still a x-coordinate and a y-coordinate, but in this case, for this virtual xy axis, xy plane. So this, let's name this A and let's name this B for the x and y. So for the cosine value, which is used for the x-coordinate, can be used together with the virtual x-axis. And previously, when we were dealing with 2D, xy, the x-axis expressed as 1, 0, and y-axis was expressed as 0, 1. Y is 0, 1, right? And when we were using the cosine value and sine value to estimate the coordinate for x and y, we were actually saying it as 1, 0 multiplied by cosine is equal to x coordinate. And 1, 0, 1 multiplied by sine theta was y coordinate. And as a result, the 0 multiplied by sine is 0, so only the y value is used and only the x value is used for the cosine, and as a result the cosine and sine was the coordinate for the circle point position. But then if you think like this, then if you replace this axis value with this virtual x and virtual y, then this can be replaced by some more general function. Like, let's say the virtual x-axis is written like, let's say x1, x2, and x3. And y-axis expressed as y1, y2, y3. Right? And the cosine theta was multiplied by the x-axis. So in this case, x-axis multiplied by cosine theta is actually going to be the actual x coordinate. and y-axis multiplied by sine theta is actually going to be a coordinate for y prime, which is this coordinate. Does it make sense? Now it sounds a bit too advanced, but if you think from a 2D, you can easily step into a 3D, and the actual equations in order to estimate the 3D positions for the circle is actually pretty easy to do. It's pretty easy to estimate. So that's what I wanted to show you, and that's what we're going to try to code here. Okay, and if you are feeling comfortable about this idea, then you're good to go with a trigonometry. You can do a whole lot of things using trigonometry for all so many purposes, right? So let's see how we can implement this. So first of all, we need to create a virtual x-axis, and that virtual x-axis can be just by using one of the directional vectors, either like direction 1 or direction 2. So let's just use direction 1, and since this is going to be the virtual axis, I'm going to normalize this so the length will be equal to 1. So I'm going to name this x-axis as a normalized direction 1. Now what we want to know is the y-axis now, so that we can estimate, we can know the virtual y, so that where this second line is lying on. To do that, one of the idea that I could think of is to first calculate the cross product of those two vectors. Now, if you remember from the previous sessions or previous tutorial, we were talking about the vectors and the cross vector. The cross product of two vectors is actually a perpendicular vector of two vectors. So in this case, we have two vectors like this. We could get the cross vectors forwarding to this direction. Well, we don't know which one is direction 1, so it could go to the other direction though. But let's try to see that. So if we calculate the cross vector of two vectors, we could calculate the perpendicular vector of two vectors, and after we have got this vectors, we can actually use it as a virtual z-axis, right? And by having a virtual z-axis, we could also try to get the virtual y-axis by using the virtual z plus a virtual x to calculate another cross vector, another cross product between those two vectors. I'm gonna explain that in the sketch. So, which is kind of a trick. So let's say this is the 3D vectors B1 and B2, right? And there's arbitrary angle here. And what we want to know, first of all, I have set the V1 as a x-axis, the virtual x-axis. Now we don't know yet what the y-axis yet, but we can estimate the z-axis using those two vectors by calculating the cross product between the V1 and V2, and then as a result, you'll be able to calculate this angle for the z, the virtual z, which is perpendicular to the V1 and V2. After we have this perpendicular vector for the z-axis, and using z and x to calculate another cross product, zx, and as a result, you get another perpendicular vector for this z and x, and that is equivalent to this y axis, right? So by having two cross product calculations, you'll be able to have all the axes you need in order to draw a circle, in order to have a virtual plane. In this case, I only need x and y, but in order to create that, I needed this z. Alright, I hope it makes sense, and let's see how I could do this. Right? So I have just we already have this x-axis. Let's say this is the x-axis, and we can calculate the z-axis by calculating the cross product between the x-axis and the direction 2, which is this one, right? Which is this another vector here. So let's also normalize this just in case. Normalize direction 2. Right. Now that we have two vectors, x-axis and the perpendicular z-axis, now what I can do now is to calculate the y-axis by calculating another cross product between the z-axis and the x-axis. Now, as a result, you should be able to create all those information in order to calculate, in order to create a virtual plane, which in this case x and y. Now we can try to create some arc here. Now we know that the maximum angle, the angle between those two lines are calculated as angle here as from a tangent 2. So I'm going to use that. We are going to use that to actually draw a collection of points like an arc from the center here. Okay, so let's do that. But first of all, I'm going to estimate or set the number of points that I want to create, creating some parameters like num. And let's set the maximum to 100. This. And let's create a for loop just like we did to create a circle or wave. And we're going to calculate the step angle from 0 to the maximum angle right here. So this will be the maximum angle. Let's say this is the axis and we want to start drawing the points from here. Then what I want to do is to create an arc like this, connecting from one edge to another edge. And the maximum angle is this angle that I've calculated using a tangent 2. And I want to divide this angle by some numbers that I have specified here. And each angle I want to plot the point, so that it becomes like an arc. Okay, so to do that, just like we did for the circle, I'm going to multiply angle by a iteration number I divided by number, and as a result you'll be able to get the value in between 0 to angle for each iteration. Maybe you might want to subtract number by 1 because I ends at number -1. So if you want to have the final angle value to be appear, then this might work well. Okay, now next thing what you can do is to calculate the length for the virtual x direction and length for the virtual y direction using cosine and sine. So the x length will be, or x coordinate will be cosine angle, or sang. Float y will be sine. Oops. Sine, Sang, Cosine, right? Now these are the coordinate on the virtual x and y. Now the final position can be retrieved by multiplying this value together with the x-axis and this value together with the y-axis, and that it's going to be the final point position for the arc. Should be. Now let's name this like tx for the x coordinate, and should be vector, and I'm going to multiply x-axis with a cosine value here, which is currently x, and vector ty for the virtual y position. I'm going to use y-axis multiply by y. Right? Now that we have two values, we can add those two vectors to create a combine two vectors for two virtual axes and to calculate the final point position. So the final vector position t pos is equal to tx plus ty. It's just a simple vector addition. And finally we could add the point to this point position. And we gotta set the number of points here. Now seems like something is okay. I need to change this to y-axis. Sorry for that. And okay, well, seems like the point position is a bit off from the second line. Let's see why. Did I change the length for the line? Nope. Okay, the reason why this has a bit of offset here is because I didn't normalize this y-axis here after calculating the cross product. Okay, so yeah, I should do that, and I also would like to normalize the z-axis, which I can just do it right here. And also for this one, normalize this so that the length will be equal to 1. And as a result, you'll be able to connect those two edges of the point, two edge for the primitive, and create a arc like this. Alright, looks good. Now let's try to change those angles, switch to the random and see if this still works. Okay, now let's try changing the seed, and even if I change to any seed, it still creates these arcs. Maybe I should move the an angle for this one to here. Should create a bit more randomized angle. Yeah. Alright, so something like this. The last part might be a bit too hard to understand for first look, but if you follow carefully what I have just talked about, you'll be able to do it by yourself as well. And if you are comfortable enough to use cosine and sine in this way, then there's nothing to fear about using trigonometry after this, and you can use this as a powerful tool for many purposes. And after this sessions, I'm going to use like this trigonometry as a basic tool to deal with other functions. So if you are not sure how this trigonometry could work or could be used, please try to look back and understand how this works. This is it for this session for trigonometry. I hope you get the glimpse of what trigonometry is and how you can actually use it for design purpose. And the next topic that I would like to talk about is Quaternion, and use Quaternion for a rotational transform. Okay, and thank you for watching. If you found this video interesting or useful, I would love to have your comment, also a like and subscribe if you want to look for other videos as well. And I have also started the Patreon myself, so if you are kind enough to support me, I would really appreciate it. Okay, so thank you for watching and see you next time. Goodbye.